Hey guys, welcome back to CMTEQ channel. This channel's main mission is to assist university students studying electrical engineering to complete their degrees with flying colors. This is why this channel is mainly focused in problem solving. This is very similar to learning by doing, so you can actually see how problems are solved. And I always cautioned that the solution provided here must not be treated as a memo, must rather understand, and so that you can repeat it when you are sitting in your exam class. Okay, having said that, we're then going to proceed in this tutorial one on three-phase transformer. The problem statement says that a three-phase 50 Hz transformer has a delta connected primary, okay, and a Y connected secondary. The line voltages are 22,000 volt, and this is on the primary side, okay, and 400 volt respectively. So the 400 is on the secondary side, which is the star side, and the primary side is the delta, okay. There is a Y connected load at 0.85 power factor, which is lagging, and the line current on the primary side of the transformer is 10 amp. So we have the transformer carrying a line current of 10 amp on its input. So now let's go ahead and start solving each one of these three questions. And at the end of this tutorial, you will have a basic understanding, rather a solid understanding of how to solve three-phase transformer problems, because they all look very similar. You just have to have a good understanding of how a transformer works, a single phase or a three-phase work, and you will do just fine. But before we continue, please don't forget to subscribe to CMTEQ channel and give this tutorial a thumbs up if you find anything useful. I thank you so very much. Okay, so the first question is draw the delta Y connection, including the load, and indicate all given information. So this is basically to make a representation of our problem statement in a pictorial form. Now let's go ahead and do just that in our solutions. So we have question A. So we need to draw, okay, the delta Y connection, including the load, and indicate all the given information. So we know that it is a three-phase transformer which has a primary connected in delta. So we're going to start by drawing each one of the phase. So we got phase 1, phase 2, phase 3 that are now connected in delta. And then we're going to connect the input voltage, which is being transmitted from the delta side, and the problem statement say that that voltage is equal to 22,000 volts. So that's 22 kilovolt. Okay, so this is the 22 kilovolt that is being transmitted from the primary side, and then we've got a line current, they say here, of 10 amps. So there is a 10 amps that's flowing here from the line. But remember, the current that will flow here and here is not going to be the same. This is why the current in your delta line is not equal to the current in each phase of the delta configurations. But now I'd like to mention one thing. Why is power always transmitted in delta? Because most transmission line are delta wired transformers, and then at the secondary, where the power now goes into the distributions, we have a star connected secondary transformer. Now the reason is very simple. First of all, it's because of the cost, because remember, in delta we only going to have 3 wires, okay, only 3 wires are going to be used for transmission, so it reduces the cost. And also the delta winding will also allow a third harmonic current to circulate within the transformer, okay, and that will be in a closed loop nature, and this will prevent the third harmonic current from flowing into the transmission line if there were actually a fourth wire that is linked into the earth. So in conclusion, power is transmitted using the delta configurations because of the cost, and also because the delta winding eliminate the third harmonic current, and also because the delta winding prevent the third harmonic current from flowing into the transmission line. Now let's go ahead and draw the secondary side, which is a star connected transformer secondary. So the phase 1 and phase 2 and phase 3 in a secondary in a star fashion. Now remember, at a secondary we also have a Y connected load with a 0.85 power factor lagging. So we're going to finish drawing our secondary side with the Y connected load on its terminal. So we've got a load also in a star fashions, and that is then connected into our transformer star windings, okay, in these fashions. And we've complete the connection of that line, and we complete another connection there. And then remember, the line to line voltage, okay, from our secondary side to the load is then given with a value of 400 volt. So that is how the configurations of this circuit is made of. So we've got a 3-phase connected load, and we have a 3-phase star connected transformer on the secondary. Now remember, in this configuration here, the line current that's flowing from the side here, from one phase of the transformer, is going to be the same current that will flow in this phase of the load. And that's going to be the same story from this line here that's going to flow into this load. And it will be the same story on this side. And that will be the same current that will flow into the load. Now we move on to the next question. That is question B. They say determine the current in each coil and in the secondary. Now we move on into the next question. That is question B, which is to determine the current in each coil, okay, in each coil of the transformer secondary and in the secondary line. Now remember, this current we already concluded is exactly the same current. But how are we going to calculate this particular current? Now remember, this is coil 1 and coil 2 and coil 3. So that means we're going to have I1, I2 and I3 flowing in these directions. So how are we going to determine it? Okay, we know that the phase, okay, primary phase voltage of the transformer is 22,000 volt. How are we going to determine this current unless we make use of the transformer ratios? Okay, now I'm going to show something very quickly here. We know that the transformer ratio, that is K, okay, KT is equal to I2, okay, over I1. But we cannot calculate KT with I2 and I1 because we don't know what is I2. We only know what is I1. I1 is given to us to be equal to 10 amps. But what is I2? So that means we won't be able to determine our KT with this formula. But we also know that KT, the same KT is equal to V1, okay, over V2. So that is also the transformer ratio. So that means from this formula here, since we know what is V1 and what is V2, we can actually calculate KT by simply calculating V1 over V2. And that's exactly what we're going to do here, since we know that the transformer primary voltage, okay, is 22,000, and then the transformer secondary voltage is 400 volt. Now remember, in the delta connection, the phase voltage is equal to the line voltage. That is why the V phase here for the primary is exactly the same as the line voltage on the primary. But the same cannot be said in the secondary, because in the secondary, the phase voltage is actually equal to the line voltage divided by the square root of 3. Now remember, the voltage across this phase here is exactly the same as the voltage on this phase. But the same cannot be said with the voltage across the two phase, because this is phase 1 to neutral, phase 2 to neutral, or phase 3, whatever the case may be. But from this point to this point is phase 1 and phase 3. So that is line to line. So that voltage cannot be equal. So this voltage here is the 400 volt. So that is a phase to phase. That's exactly like this phase here and this phase here. That voltage is 400 volt, and that's exactly the same here. But what is the voltage from this neutral point to that point? That's the one that we calculate here by doing 400 divided by the square root of 3. And based on that, we can then calculate our KT by doing the V phase primary divided by the V phase secondary. And we say that V phase primary is 22,000 and the V phase secondary is 230 times 0.94. So that is a 400 divided by the square root of 3. And that gives us a 95.26. So what does this mean? This means from here, we already now know what is the value of KT. Since we now know the value of KT, we can actually calculate I2 by saying I2, okay, is then equal to, okay, KT, right? KT times I1. Do you agree with me? Since we already found the value of KT using the voltage ratio, we can then calculate the value of I2 by multiplying KT times I1, since we know what is the value of I1. Indeed, I1 was given here to be equal to 10 amps. So now we proceed finishing our tutorial. So we then going to say, okay, the I phase primary, we know that is equal to the I line primary divided by the square root of 3. And this is, obviously, it is in delta, okay? This is in delta because in delta here, the line current here is 10 amps. But that's not the same current that is going in its phase here. Remember, this current, when it comes here, it's split into two. It goes to this phase and it goes to this phase. And that is exactly the same story when the current is coming from this position here. So it goes to this phase and it goes to this. So it's split. Okay? So that is why we say the line current divided by the square root of 3 is the phase current in the delta. And that it gives us a value of 5.77 amps. Okay? And we then going to use this value of 5.77 amps into the formula that we just demonstrated in this window here. Instead of using the 10 amp, because remember we are calculating the phase current, not the line current. So that gives us I phase for the secondary is KT times the I phase for the primary. Okay? And that gives us, KT times the phase current, and that gives us a secondary phase current of 550 amps. That is a secondary phase current where in this one here. But now remember, we said this current is exactly the same current that is going in each phase. So the line current on your star connection is exactly the same current on your star phase as well. So that means I line secondary on the star is equal to I phase secondary on the star, and that is equal to the same 550. So now we've successfully calculated the current in the coil and the current on your line or into your load, and that is equal to 550 amps. Are you with me, guys? So if you learned something, please don't forget to give a thumbs up in this tutorial. But please don't go away. We still have to calculate number C here that says calculate the transformer output power in kilowatt. Now the formula here is simple. So there are two formulas. Now your power formula is given by two formulas which must actually be equal to one another. So you either use the phase voltage, okay, or the phase values, I should say. So if you say power, okay, phase, forgive my writing, so that's going to be equal to 3 times V phase, okay, times I phase. Okay, so this formula will give you the secondary power on the output of your transformer. But remember to include your power factor, because if you don't include your power factor, then your formula will not be correct or your result will not be correct. Or you can also calculate your power in a star 3-phase transformer to be equal to power is equal to the square root of 3, okay? But in this time now, you're going to use the line voltage. So that's now going to be V line times I line. And also, indeed, don't forget to include your power factor formula so that you can get the correct value, the power factor value, so that you can get the correct value. Okay, so now here there's only two things that's different here. The number 3 here, that basically we are just adding the power that is consumed by 3 different phases of your transformer together to get a total power. Now here we are not using the phase power, but we are using the square root of 3 times the line voltage and the line current with your power factor. And the two formulas are going to yield exactly the same value. And remember, the only difference here is here and here, because this one and this one will remain the same. Okay, now let's go back to our tutorial. So to calculate the power, we know that P out total is 3 times P out per phase. And that's exactly what I just explained. So the power in each one of these phases here added together will be the total power in this transformer output. So that will then mean 3 times V phase secondary times I line secondary. We can say I phase secondary, but because we know that I line secondary is equal to I phase secondary, so it's exactly the same thing. And then that is going to be the V phase secondary is actually the I line secondary divided by the square root of 3. And that will change into the square root of 3 times V line secondary times I line secondary. And that is exactly how you calculate your power in a 3-phase star connected transformer. And this gives us a value of 323.89 kilowatt. So we come at the end of this tutorial. I hope you've learned something. Please don't forget to subscribe to my channel and drop your comment in the comment section, and come back for more tutorial like this. I thank you. Until next time. Cheers.